All right, how you doing? So how'd the ODP work out? What? Okay. So general comment, if you write your code and you test it and it works for your test cases and you assess it and you get 0 out of 10, your code is not correct. Okay? It's that simple. Which means it worked for your test cases, but there's some cases for which it does not work. And part of the challenge in coding is figuring out how to do the QA, the quality assurance on your code, how to test all the possible cases. And that's a really inexact science, right? Even more so than writing the code itself. And sometimes you can stare at your code and figure out the good edge cases, but sometimes that's hard to do, especially if your code is fairly complex. So in this problem, right, we were trying to move the first character to the end of the string. So some fairly natural edge cases would be an empty string, right, because maybe you're doing something with string length -1, and if your string is empty, that's going to be a negative index. You're going to possibly segfault, right? So that's one thing to check. A string with only one character, moving the first character to the end really means doing nothing, right? Just leaving the character exactly where it is. And that can be an edge case too. And then 2 characters, probably if your code works for hello, it'll work for 2 characters. But go ahead and try it. And while you're at it, try 3 characters, right? And try these things in different orders, because it may be that swapping the first character and the second character works fine unless you've got something else in your memory buffer, right? So maybe if you try your code on hello and then try it on something with 2 characters, you'll find out that you didn't put a null terminator in, right? And so if you can code this into a main program that takes a command line argument, right, you can try lots of cases. Or if you write a main program that just calls move, 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 move 20 times, with all kinds of different arguments, right? And you can copy these and paste them and scramble them up and make something that calls move 100 times in about 2 minutes of editing, if you like VI. And that's a pretty thorough test case, right? And chances are, if there's a problem, you'll find it in one of these edge cases. If it works on, a test like hello or something like that. But that's part of getting better at programming, is figuring out what the test cases should be and how to apply those tests. So I see some movement in that direction, which is awesome. So this was kind of the last ODP as far as these string manipulations go. But any general sort of questions or lingering concerns about manipulating strings, arrays of characters, things like that? If it doesn't feel comfortable, my suggestion is work on it some more. Right? Write yourself some code that does these kinds of things. Make something that swaps every other character. Make something that reverses a string. Make something that removes every other character from a string. Doesn't have to be something useful, right? It's just sort of practice. And there's really only a few things that you need to figure out. right, which is dealing with multiple pointers, null terminating the string, and dealing with edge cases. And those just come up again and again and again in any kind of problem like this. And the more you do these kinds of problems, the more you get proficient at dealing with those particulars. And then eventually this is second nature to you. And that's a good place. So that was my version of move. This looks hard to read. Not that I want to speak badly of sunny weather. I don't know why I saved in 0 into save, because I don't destroy in. I think I just wanted to name it something. So save is the character that's going to go at the end of the string. That for loop just shifts everything down one spot, right? And if the string has length 0, then that loop never executes, and so nothing actually gets shifted. And in that case, I will be 0, and so the null terminator will go in the beginning, but otherwise I is the last place that you wrote something into out +1, right? So presumably it's string length, so null terminator goes there. And then to avoid a seg fault, right, if I was bigger than 0, we take that saved character and we put it at the end of the string. But if the string is empty, there's nowhere to put that saved character. Theoretically, it would go before the null terminator, which would be index -1. So there's an if there to keep that from blowing up. But other than that, like I say, it's really a rotate left from 270. Any questions, comments, thoughts on high-low? I haven't looked to see how many people turned this in. Let's take a look. $62, awesome. Good turnout. 66, but there's a few people who are registered but don't seem to actively be participating in the course, so that's okay. So 62 is great. All right, so how many people have glanced at PA4? And you're still smiling, good. All right, so let's talk about PA4. So what?
Oh, never mind.
Okay. Ignore that. No, that's a bad test case. Yeah, I didn't have periods or anything. All right. Not very exciting. All right, so PA4 is basically a phrase index program. Okay, so you feed it in a bunch of text, and it tries to break your text into phrases in some sort of reasonable way. And then it produces a list at the end of how many times each phrase occurs. And the phrases are alphabetized by length. So let's see. There we go. I'll find you a test file later. It's okay. I think it's on the server. All right. So it's a high-level overview. So you're going to read lines from standard in. Okay. You're going to break them into phrases. We'll talk a lot about what phrases are. You're going to store these phrases in an array, and you're going to store an integer with each phrase saying how many times we've seen this phrase. So hello there, period, that's a phrase, gets stored in an array with an integer saying we've seen this phrase once. Today is Friday, period, that's a different phrase, gets stored in the next spot in the array, integer is 1. Today is Friday comes up again, you've already seen that, so you don't store it again in the array, but you bump up that integer to say we've seen this phrase 2 times. So you're building basically an index. Phrases, how many times you've seen each phrase. Okay. And then at the end of your input, so when you get EOF, if you're doing getChar, you take this array of phrases, you sort it by length, and you print it out, along with how many times each phrase occurred. So let me make you a reasonable test case. Okay, so there's a weird little test file, right? So if I run PA4 and I send it input, it tells me the phrase "and" appeared once, "haha" appeared twice, "I am Nick" appeared 4 times, and so on and so forth.
So you ignore spaces?
You ignore lots of stuff, okay? So this notion of what is a phrase is kind of the first battle in this assignment, okay? And there's lots of details here, but I'm going to try to explain it to you, and then you can refer to this if there's questions. These details are mainly meant to make your life simpler. So if you ignore them, not only will you lose points, but you're going to have to do a lot more work. Okay, first detail, convert everything to uppercase, okay? And you can do this using the toUpper function that's available from ctype.h. So don't look at ASCII codes. Don't say if it's little a, b, c, d, e, etc., etc. Whatever you read in, just run it through toUpper, right? And that'll convert it to uppercase. So the code?
I mean, like to run it, to make it into upper?
Do a man on toUpper. Right, so you include ctype.h. And it's just toUpper, and you just give it an integer character, it returns the uppercase version. If you give it a digit, it returns the digit unchanged. If you give it a space, it returns a space unchanged. But if you give it a lowercase letter, it'll return the uppercase letter. So you can just put everything into here, character by character, and you've got your first detail taken care of. Convert new lines, tabs, spaces, everything else into a space. Okay, and there's a function in ctype called isSpace. So when you read a character, you can say if isSpace parentheses c, close paren, c equals quote single space. That'll convert all your white space into single spaces. And this is nice Because if your input file looks like this, right, I am Nick should be the same as I am return Nick should be the same as I am bunch of returns Nick, right? So if you treat all of those as being spaces, I don't know if that'll work actually. I may be lying to you.
Let's try it.
But this should work. Right, so, got extra spaces. Yeah, I lied to you a bit. There we go. Right, so I am Nick. I'm still lying to you.
There's a lot of extra spaces.
There might be a space after Nick period.
This one will work, I guarantee it. There we go. Right, so the idea is if your line is broken up, right, so you're running this on War and Peace as a test case. So if a sentence comes to the end of a line and continues on the next line, right, you don't want to treat that as two phrases. So that new line character gets turned into a space and it looks like just a big long line. So so anything that's a white space, change it into a regular space, okay? And that's one line of code. Ignore parentheses, single quote, double quotes, and dashes. Okay, if you see one, ignore it. Don't put it into your output, don't use it to break up phrases. It does not exist, okay? It's not part of your universe. So if you're reading your input and you read a parentheses, a single quote, double quote, or a dash, pretend you didn't read it. Just read another character. If it's another parentheses, ignore it, read another character. Okay, so those are not part of our character set. Okay, so what is a phrase? A phrase begins with any non-space character other than these particular punctuation marks. And then it's followed by a set of consecutive letters or spaces, but none of those punctuation marks. And then it ends with one of those punctuation marks. Okay, so phrases are basically things that end with punctuation. And once that punctuation ends, right, you ignore any spaces after it, and when you get something that's not a space, that's the beginning of the next phrase. And it's a little bit of a heavy-handed definition. But let's say this is your input. So it begins with a non-space character other than punctuation. Okay, so this is the beginning of a phrase right here. And then it's any collection of characters, including spaces other than punctuation. So, and punctuation is comma, period, semicolon, etc. So it's going to include all of this until you get to the comma, right? And the comma marks the end of the phrase. So this is one phrase. All right, and then your next phrase begins with a non-space character other than punctuation. So it's not the comma, it's not the space, it's the T right here. And it's any collection of characters or spaces that are not punctuation. And so when you get to the period, that's a punctuation. So this is your next phrase.
What if it's like an apostrophe?
Apostrophes are dead to you. They do not exist. So you can throw in a bunch of apostrophes here and parentheses and all that, and those don't appear in your phrases. Okay, we're going to talk about how to ignore those. All right, so leading spaces are not part of a phrase. Spaces inside your phrase are part of your phrase. Punctuation is not part of a phrase. So how is a phrase? Now is a phrase. Okay is a phrase.
When it's starting inside of the phrase, do we check for, since it has multiple spaces from what it looks like, do we put multiple spaces?
Multiple spaces don't appear in the beginning of a phrase, but
No.
inside a phrase, yes.
Okay.
If it's
inside.
so 5 spaces how, that's so 5 spaces how.
Okay.
All right, so this is the weirdest part, and it's supposed to take input that looks reasonable and break it into phrases that look reasonable. It's not perfect, okay? If I made it perfect, it would be like 5 pages of description. but it's a specification that hopefully you can work with. So begin with a non-space, non-punctuation, go until you get to a punctuation. That's a phrase. Okay, save the phrases, save the number of times they occur, and then at the end, print out your list of phrases sorted by length and the number of times that each phrase occurred. So, pseudocode. Read from standard in until you find the beginning of a phrase. This is a state machine. Okay, so your first state is we're looking for the beginning of a phrase. When you find the beginning of a phrase, keep reading from standard in until you get to the end of a phrase. So that's your second state. We're ingesting a phrase. And as you read these characters, store them in a temporary array somewhere. Build up a string, right? When you hit the end of the phrase, throw a null terminator on so that you have a bona fide string. And then see if that phrase is in your dictionary, your array of phrases. If it's not, add it to your array of phrases, set the occurrence count to 1. If that phrase is in your index, just increment the occurrence count. And just repeat those first 3 steps till you get to the end of the file. That builds your array of phrases and counts, and then sort the array, print out the array, and you're done. Make sense so far? Okay, so there's an asterisk where I say read from standard in. So here's my next strong suggestion. Make your own version of the getChar function. Okay, getChar reads 1 character from standard in. You don't want to use getChar. That's too crude. Make your super duper version of getChar that does the following. It ignores those magic characters. It converts any white space character to a space, and it changes every letter to uppercase. And forget about getChar after that. Just call my super duper getChar, right? And now you don't have to worry about those 3 things. You don't have to worry about ignoring those marks. You don't have to worry about converting white space, converting to uppercase, because my super duper getChar does all that for you. Okay? This is modularization. So first thing you might want to do is write your version of getChar. And then feed it some stuff with parentheses, with tabs and new lines and lowercase letters, and convince yourself that it's doing those 3 things. Right? And now you can safely ignore all of these details up here. Right, those 3. And all you got to worry about is parsing out phrases. Okay, further simplifying assumptions. You can assume that a phrase is 200 or fewer characters. If a phrase is longer than 200 characters, just ignore everything after the 200th character. And you may find some phrases that are 500 characters long, right? Just take the first 200, that's your phrase. And you can assume that you're going to remember a maximum of 1,000 phrases. Okay? With these 2 restrictions, you don't need to deal with dynamic memory. You don't need to do mallocs. Okay? You can make your dictionary 1,000 entries long with each phrase 201 characters. Right? 200 characters and an null terminator. And you don't have to do things at runtime. If you have 5,000 phrases in your input file, don't exit your program after you find 1,000 phrases. Okay, process the whole file, but you don't have to remember anything other than 1,000 phrases. But you've got 1,000 phrases, there's more input, there's new phrases. If you encounter an old phrase you've already seen, go ahead and bump up your counter. Okay, don't just give up when you see 1,001 phrases, but don't save anything other than the first 1,000. All right. That's really pretty much it. Here's a sample file you can work with, but use your own test cases. If you use this file, here's what your output should look like. Okay, so that's a test case for you, but it's not the only test case you want to use. And when you're developing this, you probably want simpler test cases first anyway. All right, and then some hopefully helpful suggestions. Break your program into pieces. Okay, don't try to write this as one big monolithic program, because there's lots of details in here that can be farmed off into subsections. For example, my super duper get car, right? Code that up once, and then you can just call that anytime you want a new character, instead of repeatedly looking to ignore characters, converting, et cetera, et cetera. So top-down design methodology says we write our main program first, and the main program basically just calls some functions. And then we write those functions, and they really just call other functions. And we write those, and they call other functions. And eventually we get down to something that actually does something, right? Bottom-up methodology says, okay, first I'm going to write my super duper get car, and then I'm going to write my get a phrase function, and then I'm going to write something else, and you're going to kind of build up. And usually there's a mixture of those that we do, right? Some things might make sense to start from the very bottom details and build up. Sometimes we start from the main program, we work our way down. And it's probably a combination of those, right? So find a happy space in terms of where you want to be, top down versus bottom up. But definitely think about being modular, right? Think about breaking things into pieces. And we'll sketch out some pseudocode and write some pieces in a moment. Think about your algorithm though, right? We've gone over the algorithm basically, but think about it in terms that make the most sense for you. And develop and test as you go, right? Don't write 15 functions and 1,000 lines of code and then do GCC for the first time, right? Right? Build these things as you go and test them as you go, okay? So some suggestions for pieces that you want to build: a way to read standard in and pre-process the character. That's my super duper get car, right? A way to detect the beginning of a phrase. How do we detect the beginning of a phrase? Well, it can't be a space, it can't be a punctuation, right? Well, that's just a big if statement, right? But if you put that into a function called, is this the beginning of a phrase, right? When you get a character, you can say if, is this the beginning of a phrase, parentheses character, and then say what you're gonna do. And you know what, if you mess up on what the beginning of a phrase is, you forget that you're supposed to ignore spaces, you just change that one function, right? As opposed to trying to find everywhere in your code that you use this assumption, right? So that can be a separate function, a way to detect the end of a phrase, right? Is this the end of a phrase, parentheses character? And it gives you back a true or a false. And then storing a phrase in a dictionary, sorting and printing, right, are pretty obvious pieces. You're going to want a ton of comments in this, okay? No matter how good you are at coding, your code will not be self-documenting. Okay, you're going to want to explain everything that you're doing in here. You may want these functions in separate files, okay, just to sort of minimize the compile job. You may want to make file for this. Whatever the pieces are that you end up with, right, put them all into a tar file, upload that through Canvas. That's your submission in this case. So it's just a .tar. And make sure you know how to tar files before the night that you're ready to turn this in. Don't destroy your code, right? And tar files are a good way to do backups anyway. So what might this look like? So here's some high-level pseudocode. Read a phrase from your input. Save in my index of phrases, and loop. And when there's nothing left to read from the file, sort the index, print the index, and you're done. There's your main program. Yeah. Take off 2 weeks now. Right? So logically, to me, that makes a lot of sense what this program's going to do. Right? It doesn't do it, but it's how I personally would think of this, right? Read a phrase, save it in my dictionary or my index, keep doing that until there's no more phrases, and then sort it and print it. All right? So if I call that my main program, it gives me kind of a skeleton on which to start adding some more actual code, right? So how do you read a phrase? I don't know.
Well, we have to know when reading a phrase is that whether it's one of the punctuation marks.
Okay.
Or a letter or a character.
Okay. And reading a phrase, I don't know, there's different ways you could do this, but you could make something called getPhrase that you pass a character array to, and have getPhrase return an integer telling you if it actually found a phrase or not. And maybe this integer, 1 means you got a phrase, and 0 means you hit the end of the file. So now I could say, while getPhrase phrase, save an index parentheses phrase. It's a 2-line main loop. And then sort parentheses index, print parentheses index. All right, but you can do this however you like. In my main program, phrase only has to be 201 characters, right? Because a phrase is 200 characters plus a null terminator. So if I make my phrase array, 200 some, I can just pass that to my getPhrase code. So phrase begins with a non-space character other than punctuation. It's a collection of consecutive letters, and then ends with a phrase ender. So I'll call my super duper get car, right? And I'll save that in C. If C is not the start of a phrase, I'll go back up here and get another character. And I'll keep doing that until C is the start of a phrase. And maybe I'll do an output index, which I'll initialize to 0. So once I get a character that's the start of a phrase, I might say out index ++ equals C. So that copies my character that is the start of a phrase into my output array and bumps up out index. And then I'll get another super duper character. And if it's not the end of a phrase, I'll save it in my output index. And I'll go back up here. And if that character I got is the end of a phrase, I'll just go ahead and null terminate my output array, and I'll return 1. And then you got to do something in here to detect end of file. Because ultimately, when you get to the end of a file, you want to return a 0 instead of a 1 to say, hey, there's no more phrases left. But you can do that right up here if you like. Right, so think about how to do that. But if you set up your super duper get car to handle end of files a certain way, you can detect that you hit end of the file because your phrase will have a length of 0. So there's ways to do that. But anyway, that's a basic pseudocode for reading a phrase, right? And it's built on top of this idea of being able to tell if a character is the start of a phrase or the end of a phrase. So start of a phrase is not a space, not a punctuation. End of a phrase is punctuation. And then how do you save in the index? Well, you can either use structures or you can use parallel arrays. I'll do this with parallel arrays because we haven't officially talked about structures. But we can have an array of characters 1000 by 201. That's your actual index. We can have an array of integers, that's 1000, that tells us how many times each phrase occurred. And remember, with arrays in C, there's no inherent length, so we need to know how many entries we have in this index. So we can do an index length. And initialize that to 0. So the basic setup is index is this big long array of strings. It's got 1000 strings. Each string is 201 bytes. Count is just an array of integers. And index len tells you how much stuff you have in these arrays that's meaningful. So it starts off at 0, you get your first phrase, which is hello. The count will be equal to 1, index length will be 1. You get your next phrase, which is bye for now. And that's got a count of 1, and index len is equal to 2. So at any time, you can look at index len and say, I have 2 phrases in my index. It must be the first 2 entries. This is how many times I've seen them. Now you call your read a phrase, and it comes back with the string hello. And so you say, let's save hello in my index. And what you want to have happen is hello gets compared to this, and it says that phrase is already in here. So instead of storing it in the 3rd entry and bumping this up, we say it's already here, let's just increase this count. And the next phrase is hello again, you see that's in there, you increase this count. The next phrase is bye for now, you see that's in here, you increase this count. The next phrase is cool, and it's not in here, so you make a new entry, you set the count to 1, and you increase your index length to be 3. Make sense? So this is nothing that you haven't already done at some level in 121, and certainly in here, right? It's a lot of pieces.
Would you have to compare it character by character, or is there a way just to check?
So you can compare character by character, and I think I tell you can use string compare. So you can use routines from string.h. So there's this thing called string compare. Right, you pass it two strings, it'll tell you if the strings are the same or not. And what you want to look for is a return value of 0. Okay, compares two strings, returns an integer less than, equal, or greater than 0 if S1 is less than, the same, or greater than. So if you want to know if two strings are the same, pass them to string compare, see if it returns a 0. If it returns 0, they're the same. If it returns non-zero, they're different. Or you can write your own version of string compare, but you don't have to. All right, so how do we save a phrase in an index? So let's just iterate over the length of our index, right? The number of things in our arrays. If index if entry I in our index matches our phrase, right? So string compare, then increment, what did I call it? Index count, I just called it count. Increment the count and return. So that takes care of the case that we've got a phrase that's already in there. Bump up the count and return. Otherwise, check the next phrase. So we keep going through this. We get out of the for loop. If we come down here, we have a new phrase. Okay, at this point we can say if index len equals 1,000, we're just going to return. Because we've got 1,000 phrases in our index and we just found a new phrase, we're not going to store it. Okay, so this kicks us out, and the caller has no idea that we didn't actually store a phrase. That's okay. Otherwise, we want to store our phrase, so what do we do? Copy phrase to index len, right? And you got to be careful about the edges here. So with this setup, index len is 3. If we get a new phrase, we want to store it right here at index 3. So index len, the way I've set this up, is always the location where you're going to store the next phrase. You might do it differently, okay? But whatever your interpretation of index len is, right, use that to figure out where to store. So in this case, I'm going to copy the phrase to entry index len. And then I'm going to say count index len equals 1. So that sets my count to 1. And then increment index len and return. And there's your whole save phrase and index code. So when you're breaking a program or a task into pieces like this, right, it's important to have a pretty good idea what the behavior of those pieces are going to be at a high level. You don't necessarily need to get down to pseudocode at this stage, but you want a really clear idea in your head of what does read a phrase mean, what does save an index mean, right? So I'm going to make something called get phrase, and I'm going to make something called save an index. What are the behaviors of those, right? You want to write those out, probably just plain text, right, somewhere, so that you know exactly what the responsibilities of each of these functions is, so that you know if this is going to do enough so that I can call it inside my main program, or I can call this inside my loop over here, right? And then at some point you want to be able to like put down code to actually perform whatever that function is. But make sure you understand how these pieces go together. Right, so what are you going to pass in? What's the function going to do? What's it going to pass back? So what do we have left? Well, we got to sort and we got to print. Printing is easy, right? If you want to print your index, you just go from 0 to index len, you print count bracket I inside angle brackets, and you print index bracket I, right? So sorting we have to talk about. You can do a bubble sort, and we'll refresh on a bubble sort on Monday, but bubble sorts are fine. So to test this as you're developing, right, you don't need to have your sort routine working to test all the other pieces, right? You probably want your print method working, and printing is just a for loop, right? So you can throw that together pretty early, and you can forget all the super duper get car stuff if you want, if you don't feel like writing that first. Treat uppercase and lowercase differently, treat different kinds of white space differently, don't ignore parentheses and quotes. You can choose, you know, to live like that in the beginning. That's perfectly fine, right? And in your test cases, you know, maybe just use uppercase letters and don't put in parentheses and weird characters, right? And if you want to concentrate on trying to parse your input into phrases, right, just use a test case that makes that easy and work on this code. And now make a main program that basically just keeps pulling in phrases and prints them out. So call your read a phrase and print it out and keep doing that. There's our read a phrase. Yeah?
Did you say the program reads in a phrase from the argument line, or?
No, it reads from standard in. There's no command line arguments for this program.
Okay.
So it just keeps reading from standard in, ultimately using get car.
So we don't take a file, it's just static.
You don't take in a file. If you want to test it with a file, just run your program with a less than sign in the file name. So if you go on the Linux server, I don't have it up there. I'll put War and Peace up there for you. War and Peace is a great test file, right? Because it's really big. And what you don't want to do is read the whole stream of input in and try to store it in memory and then start processing it. Okay, because I guarantee I'll blow it up. Okay, read in your characters one at a time, break them into phrases, process those phrases as you're reading. Okay, that's important, because otherwise you'll definitely run out of memory. All right, questions about that? So kick it around, ask some questions, and start writing pieces of your solution. And we'll talk about sorting on Monday.
I have a question. So for 8